start recording. Okay, so take a moment to copy the example down, class. Take a moment. Okay, so here in this problem, well, so we learned in the last class with section 6.1 how to manipulate the power series and combine power series with different indexes so that we can get a more simple expression. And just a quick comment, class, while I'm at it, in the homework that was due today, that last problem in section 6.1, that the red number is a multiplier on that second series. It's not a power. Just thought I'd mention that because a few students asked me about it. On the homework that was due today, the last problem, the red number, it's not near the second series. It's a multiplier on the second series. It's not a power. Okay, all right. So let me ask you. Is this a simple? This is what's the order of this differential equation? Y prime plus y equals 0. What order is it? First order. Okay, so good. What's the auxiliary equation? That's right, Antonio. What's the auxiliary equation? It's a homogeneous differential equation. Okay, good, Zachary. M plus 1 equals 0. So that means M equals, good, -1. And so the solution, the general solution, which will equal some constant, good, that's right. It'll be some constant times e to the -x. That's right. So using the techniques that you've already learned in chapter 4, this is a very easy solution to get. But you see, the techniques that you learned in chapter 4 for solving second order and higher order linear differential equations all involved, all those problems had like constants in front of like the derivatives and the y on the left. You didn't have functions of x as coefficients of like any derivatives or you didn't have a function of x as a coefficient of y. They were all constants, okay? And in applications, we need to be able to deal with situations where, what if we had something like this? What if we had, well, and I want to be a little careful because you have learned about integrating factor and separation of variables, but like what if you had x, y double prime? What if you had this differential equation, x times y double prime plus y prime minus 2y equals 0? This is a second order differential equation. Okay, a second order linear differential equation. But the coefficient of y double prime is x. And so that situation where you have a variable, or you could have an x squared there, for instance, any function of x, right? But the techniques you learned in sections 4.3 and 4.4, the undetermined coefficients technique, won't handle these kind of situations where you have a variable function as one of your coefficients. And this is why we need to learn about finding solutions as power series. Okay? All right, so that being said, let me go to the next page here. Are there any questions so far? Okay, well, all right. So let's think about this power series. So the power series, maybe I'll put it in blue, is equal to the sum where, hold on. Hold on. Okay, this is your power series. Okay, one moment here, class. Let me plug my thing in here. Okay, so, all right, and this is just c sub 0 times x to the 0th power plus c sub 1 times x to the 1st power plus c sub 2 times x to the 2nd power plus c sub 3 times x to the 3rd power, and so forth. Okay, keeps going. All right, keeps going. So what we want to do, of course, is we want to substitute in the power series in our differential equation. And so that means that we have to take the derivative of the power series. Well, what does this notation mean, this sigma notation? What are you doing to the terms in this power series? What's that sigma, that Greek sigma notation mean? What are you doing with the terms? It's a summation. That's right, Zachary. So we are, if we want to do y prime, all right, we are taking the derivative of a sum. And the derivative of a sum is the sum of the derivatives. Now keep in mind, the only variable here, is the x, right? The c sub n is it's a constant. Well, it changes as n goes, as you go through the values of the index, 0, 1, 2, 3, 4, 5, and so forth. The constants, c sub 0, c sub 1, c sub 2, c sub 3, c sub 4, and so forth, they're going to be different values, right? But we're not worried about that yet. So, okay. Now, now I have here, please let me know if you have any questions. I have the derivative of c to c sub n times x to the nth power. Well, c sub n is a constant relative to x. And so I factor it out. And the derivative of x to the nth power, okay, the derivative of x to the nth power is just by the power rule, n times x to the n minus 1 power. Let's see, Zachary, which step? So let me see here. Hold on. I'll put down steps 1, 2, 3. Oh, the first step, or point it to me with the pen. Oh, you mean okay, hold on. Zachary, are you referring to this step here? Okay, so this is no different than if you had f plus g prime. That's going to equal f prime plus g prime. The derivative of sum is the sum of derivatives. So what do I have here? What do I have here? I have a sum. Right? Well, let me be more clear. I have a sum. I have a sum here. And I'm taking the derivative of that sum. So that's going to be the sum of the derivatives of each term. Is that okay? Feeling a little better, Zachary, with that? Okay, good. So then, we just sort of use our calculus and we get down to here. Okay, now, something interesting happened here. The index started at n equals 0, and now it got changed to n equals 1, just like that. Think about that. Why are we able to do that? Let's see, there's a chat thing here. Antonio, that's right. If you look at the terms of the series, c sub n times n to the x to the n minus 1 power, when n is 0, you're going to have this. Hold on, I'll put it in use my stylus here. If I were to write this out, I'd have c sub 0 times x to the 0 minus 1. And then the next term would be c sub 1 times x to the 1 minus 1, and so forth. Well, so what happened here is that you have a 0 here. And so when n equals 0, that term is 0. So you can start the series, therefore, at n equals 1. Okay, are there any questions? Any questions up to that step there? Hold on, think about it for a moment. Hold on. There we go. All right. Well, third step. All right, so the third step here Another good question. The third step here, I'm taking the derivative of c sub n times x to the nth power. Well, c sub n is a constant, right? So a constant can be brought out in front of the derivative. It's still a term in the series. It's just.
Wait, yeah, so it's a constant with relation to n? Because, like, otherwise, why wouldn't we just call it c rather than c sub n?
That's right. Well, you see, good question. I mean, you're taking an infinite number of derivatives here. Every term you're differentiating. But c sub n is a different constant for each term. It could be the same, but it could be different too. You have to allow for that.
Okay, so it's got the variable n there, but not the variable x, which means it's a constant in terms of
exactly
dx.
Right. With respect to x, it's a constant. Yep. Yep. Okay. Well, if we're feeling good with that, let's move forward here. Let's move forward. So what I'm going to do is I'm going to substitute in my derivative and my original power series. They're both, the derivative is a power series. But then keep in mind, we want to have the same power in each series. We want to have the same power. The first power is n minus 1, the second power is n. So that means for the first series, I'm going to let k equals n minus 1, and for the second series, I'm going to let k equals n. Let me give you a moment to catch up here. One moment. Okay, so now what we're going to do is, it's sort of an amazing result. You know, well, are there any questions on how I got the c sub k plus 1 here and the k plus 1 there on that first power series? I mean, if k equals n minus 1, then k keep going back and forth here between my k plus hold on, guys. All right. So if k equals n minus 1, then k plus 1 equals n. And so that's how I get those guys there. Hold on, there's a question in the chat. One moment. Okay, well, so now what I want to do, so what I want to do, Zachary's wondering about why my, all right, so the third step, you mean this step here? What I'm doing is I'm combining the power series. The power series both start at k equals 0. So I can combine the power series and write the power series like this. Let me see now. So Zachary, I want to meet your question's a good one. I want to make sure I've answered it. Are you maybe with your with the mouse point to where you're a little uncomfortable?
Basically, what I'm trying to ask is that on our last page, we shifted the summation by 1 from 0 to 1. However, if we were not to do that, the first summation in the bottom left corner right here would be k equals -1.
Right. So you want to do this. You want to make that change because where we dropped the first term, we just started the derivative, the power series for the derivative. We started it at n equals 1. You want to do that. But if you had not done that, it should still work out. But you generally want to do that. And incidentally, if you're going to take the second derivative of a power series, what value of n do you think that would start with when you drop out the 0 terms for a second derivative of a power series? That's right. That's right, Antonio. N equals 2. Okay, for the all right. So we just having like 0. Our power series. We don't want our power series to have terms that are 0 in it because that's not interesting, right? So we want to simplify the power series before we substitute it in the differential equation. And the derivative, the power series for the derivative, could start at n equals 1. And it turns out it was very handy that it did, because then when we re-indexed our power series, they both start off with the same k equals 0 index. It's beautiful, really. But what we want to do now, remember, the general solution to this differential equation, we already know it equals some constant times e to the negative x. I mean, that's true. That's what the general solution is to our differential equation. So can we get a power series representation of this solution here using, by manipulating through the power series? And the answer is yes, because what I'm going to do is I'm going to factor out in this term here. I have a common factor of x to the kth power. I can factor that out and rewrite the power series, or what is this equal to? This is equal to y prime plus y. I can rewrite the left-hand side of my differential equation like this. So y prime plus y is equal to this power series. But now I want to solve for these unknown constants here. I want to solve for them. So what am I going to need to set the power series equal to in order to solve for these CK and the CK coefficients? What am I going to set that power series equal to? What must I set it equal to? Well, what was the original differential equation? Original differential equation was y prime plus y equals what? Equals 0. That's and that's how I got my solution, y equals c times e to the negative x power, right? Well, okay, similarly, I'll set the power series here on the left equal to 0, and hopefully I can solve for the coefficients. Are there any questions before I move to the next page? Okay, okay. All right, Christopher's good. Very good, very good. All right, well, so now I set the power series equal to 0, but the only way that entire power series on the left would equal 0, and remember, you got the x to the kth power there, but we want this to be equal to 0 no matter what x is, right? So the coefficients would all have to equal 0. They'd all have to be equal to 0. And we get this recursion relationship between c sub k and c sub k plus 1. It turns out c sub k plus 1, the k plus first coefficient, is equal to negative of the kth coefficient divided by k plus 1 for k equals 0, 1, 2, and so forth. Let me give you a moment to catch up here. Please let me know if you have any questions. Okay, hold on here. I hear something here. Oh, okay. Where did the 1 go? The orange arrow. These here, these are parentheses. These are parentheses here. These are these parentheses. Oh, good catch. Okay, good catch, Zachary. Class, this here, this C sub k in front here, that should indeed be C sub k plus 1. Okay, so please correct that in your notes. Thank you, Zachary. That should be C sub k plus 1. And let me correct it in my notes too. Okay, so now what we want to do, now that we have this recursion relationship, we have this recursion relationship here, we can start identifying what the coefficients are going to be. So I'm going to let, I mean, you know, I start off with C sub 0. I have to have some starting point. So C sub 0 is some coefficient. Okay, well, what would C sub 1 be? Well, C sub 1 is, you know, what's k equal to? Well, k would equal 0 for C sub 1 because the left-hand side is of my recursion relationship is C sub k plus 1. Well, all right, if I have C sub 1, that means k has to be equal to 0 because 0 plus 1 is 0. So C sub 1 will equal negative C sub 0 divided by 0 plus 1. K is 0. And that's going to equal negative C sub 0. C sub 2, the second coefficient, well, all right. Well, since 1 plus 1 equals 2, k equals 1 there. So that's going to equal then by this recursion relationship, C sub 2 would be negative C sub 1 over 1 plus 1, which is negative 1/2 times C1. Oh, but what's C1? C1 is negative times C sub 0. So C sub 2 then, it turns out, is 1/2 C sub 0. Are there any questions so far? All right, well, we can keep going here. C sub 3 is going to equal negative C sub 2 over 2 plus 1. So that's negative 1/3 C2. But C2 by the second equation there, C2 is 1/2 C0. So C3 is negative 1/6 times C sub 0. And I do one more here. I mean, we keep going, we can keep going, but we get enough terms. C sub 4 will equal negative C3 over 4, okay? And, but C sub 3, we know that equals negative 1/6 times C sub 0. And so C sub 4 is 1 over 24 times C sub 0. Let me give you a moment to copy that down and think about it. That's right. So you're starting to see a factorial. You're starting to see factorial behavior in the denominators. 2, incidentally, is 2 times 1. We could all, 3 times 2 is 3 times 2 times 1. 4 times 3 times 2 is the same as 4 times 3 times 2 times 1. I mean, you're getting factorial terms down here. Very good. Very good. All right, let me let you think on this for just a few moments. Okay, are there any questions before we move to the next page? Okay, all right. Well, so what we're going to do, now that we know some coefficients here, we're going to go ahead and write out our solution a little bit. So on the next page, what I do is y, our solution y is a power series, and these are the first 5 terms of the power series. And I just substitute in, C sub 0, C sub 0, but C sub 1 is negative C sub 0. C sub 2 is 1/2 C sub 0. C sub 3 is negative 1 over 6 C sub 0. And C sub 4 is 1 over 24 C sub 0. Looks like we're getting an alternating power series here. Let me give you a moment to copy. Okay, so what I do now then is I factor out the c sub 0. All of these terms here, all of these terms have a c sub 0 in them. So I can factor that out, and I can write the power series this way. And then I recognize, as Zachary noticed, and I'm sure some of you noticed as well, we're getting factorials here in the denominators of our terms. And so I can write, I mean, I have my infinite power series written out, the first 5 terms of it written out here, but I can then write it in condensed form now that I know the pattern of the power series. And so y is going to equal this constant c sub 0 times this power series, where n equals 0 to infinity of -1 to the nth power times x to the nth over n factorial. Well, that power series is actually the power series for e to the negative x. That's the power series for e to the negative x. Let me show you why. Let me show you why. I'm going to come back to this page, but let me just show you why. I better go to the whiteboard here. I'll come back to the page because I've been getting a few questions on that. So if in section 6.1 you have a table of Maclaurin series, and one of the series, whoops, hold on. One of the series is this. Hold on, let me, one moment, class. Let me get the right page. I mean, I know the series, but I just want to. Maybe, let me see here. One moment. Let me bring up the ebook. Wait, ebook. Okay, I'm going in, and you have your ebooks. I'm going into section 6.1. Yeah, this is what I want. So let me share my application here. Okay, double click on it if you want to make the screen a little bigger. So how many recall this in Calculus 2, seeing the Maclaurin series? These are some very common ones. It comes from, we have a table in section 6.1 that has these type of power series. How many recall like e to the x, cosine of x, sine of x? You don't have to remember those power series. You could always use them like on you know, like your next exam, you could use those as a reference. Sure, Andre remembers somewhat. Gosh, I hope more than one person though recalls these a little bit. I'll sleep better if maybe 2 or 3 other people. All right, Christopher recalls it. All right, Zachary. All right. So again, you know, we can represent functions as power series. So the power series for e to the x is at the top. And what I'm going to do, I'm going to go here to the whiteboard and write down that power series. Oh, I'll mention one more thing too while I'm at it here. Every power series, you notice has an interval of convergence. So like for instance, the first power series, e to the x, the power series for e to the x, the interval of convergence is -infinity to infinity. So that means e to the x will equal that infinite series for any x value. But on the other hand, if you go down a little bit, like to the arctangent, the arctangent of x equals that power series only when x is restricted to be in the closed interval from -1 to 1. And of course, you can establish the intervals of convergence by what special test? What special test did you learn to help you get the intervals of convergence? We learned it in the last class. Begins with an R. The ratio test. That's right. Good, Andre. Good, Hyung. That's right. And of course, you still have to test the endpoints, but of the interval. But yeah. So let's see. Matthew says these are series with infinite intervals of convergence. No, series with infinite intervals of convergence. The series converge for those x values. The series will equal the function over x values that are in the interval of convergence. Yeah. However, the series diverges outside the interval of convergence, meaning it can't equal the function then for x values outside the interval of convergence. Excellent question. Excellent question. Okay, so now well, Zachary, for convergence, we do need fractions to get larger on the bottom, but it's not enough. But let me just write down that power series for e to the x. Okay, I'm trying to write it. Yeah, so if you have e to the negative x, okay, all you need to do to find the power series for e to the negative x is substitute in negative x for x. I like to think of it like this. I like to think of if I had e of an apple. Okay, e of an apple. Well, all right, what would the power series be for e to the variable apple? You just plug in apple where the x goes. See that? So e to the apple equals this power series. And so e to the negative x, well, the negative x then is my apple. And so it goes in here, as you see it. But naturally, we want to simplify this a little bit. So negative x is like -1 times x. We're raising that to the nth power. And that's the same as -1 to the nth power times x to the nth power. Sorry, I need my factorials, right? The bottom. So e to the negative x that exponential function will equal this power series. Are there any questions on that? Before I go back to the solution? All right, let me go back to the solution then. All right, and so in our solution, we found that the solution to the differential equation can be written as this power series, but that's just a constant then times the power series for e to the negative x. And so look, we got the same solution. Remember, we said that the solution, when we did it like using the auxiliary equation, the solution to this linear first order differential equation was just c times e to the negative x, right? That's what we said it would be, and it is. It is. We just have it written in terms of a power series. And we'll note that the interval of convergence for this power series is also from negative infinity to infinity. Okay, let me give you a moment to copy that down. Let me know if you have any questions. All right, are there any questions? Any questions in general on this kind of problem? How many think it's really kind of beautiful, this idea? A power series solution to a differential equation. I I was hoping I'd get more, maybe a few more response. All right, thank you, Wajia. All right, thank you, thank you. Um, you know, it is incredible. And what will happen, like in WebAssign for these kind of problems, is normally they have for most of them like multiple choice, where they give different power series, and you have to find the right one. You have to work it out and find the right one. So because it does take time to type all that in, but there may be a few where you type in the series, but I think a lot of it is multiple choice. Now, of course, we solved a first order differential equation. What we're going to learn next week is how to solve second order differential equations using power series. But this was a nice introductory example, and I haven't posted an assignment, a section 6.1 assignment, a second assignment that relates to what you learned today, but I will. But remember, the exam will only cover the section 6.1 assignment that was due today. All right, let me give me just one moment here to I just need a moment to make an adjustment here so you can see your grades. One moment. And let me stop the recording too. Let me do that.